Alright, so this is going to be example 7.3 from your textbook. Statics, 14th edition. Does anybody not have the textbook right now? Like, with you? So everybody has a textbook?
I have the textbook.
Awesome. That's good, that's good. So, that's good because, you know, since we're not going to have actual lectures, I think you'll get more from the textbook that you can get from my review sessions. But who knows? So in this example, let's see, they're giving us a beam that is connected to a hinge and then connected through a bar. So we had a similar example to this one a couple of chapters ago. I'm not sure you guys remember. We had a bar and that bar was connected to another hinge. We have a distributed load that's rectangular acting on the beam, and this load is 50 pounds per foot. The beam is 8 feet in length. I'm gonna have to write that somewhere. And from the beam down to this bar, we will have 6 feet. So I didn't actually draw this correctly. This bar should actually extend all the way down here. So this is my hinge. Okay. So essentially we have 6 feet in the horizontal for the bar and 8 feet in the vertical. So now, given this information, what is the normal force, the shear force, and the bending moment acting at point B? Where point B, I'm going to call this B, is going to be right in the middle of this beam, so it's going to be at a distance of 4 feet. Okay. So, yeah. So given this information, we want to find the internal forces at point B. So, step 1 for these problems is always going to be to draw your free body diagram. We have two bodies in this system. We have a beam and we have a bar. So if you want to draw a free body diagram for this particular problem, which one of these would you choose?
Your beam?
Yep.
Or beam.
Yeah, you want to choose the beam, not the bar, because first of all, your point is at the beam, and second of all, you already have a force acting on the beam, and you have this force acting. You have most of the forces already acting on the beam. So you want to choose your beam. So, free body diagram. We have this distributed load right now, but I wanna kind of like jump the curve and reduce that distributed load into one force. So this is a rectangular distributed load of 50 pounds per foot acting over all of the 8 feet of this bar. So if we want to reduce that load into a force, what would that be?
That would be 200 pounds per foot.
Close. This is a rectangle. So the area of a rectangle is going to be the base times the height, right? So in this case, the base is 8 feet. The height is 50 pounds per foot. So 8 times 50 is 400. Does that make sense?
Yeah.
Okay. And this is rectangular, so we know that the point force acts along the centroid. So for a rectangle, where's the centroid?
The middle.
Yep.
The middle. Yeah.
Right down the middle. So we have 50 pounds per foot times 8 feet. The feet cancel out, and that gives us 400 pounds, and that is acting down at the middle, which is 4 feet from the left. Okay, so as far as free body diagrams go, I gotta show all the forces acting on this beam. So what forces am I missing?
Maybe the hinge.
The hinge? Okay, so the hinge,
Yeah.
that gives me an X and Y force, right? I'm gonna call, I think this is point A, and this is point C. So I'm gonna call this AY, and I'm gonna call this AX. This is an external force. I can select my arrow however I want. If I get a negative value, I just selected the wrong direction. Okay, so AY and AX. Is there any other force acting on this beam? So right now this is a hinge. So if these were all the forces, then there would be no equilibrium. So how do we have equilibrium? What force am I missing?
From the second beam?
Okay, so we have the second beam, right? So we have this beam, this bar, which is exerting a force on the beam on top. A bar is not like a cable, right? A bar is a rigid body, which means that it can only act in tension or compression. So just by looking at this system, you can see that we are applying a force that's making this rotate, and this bar, if this system is stable, this bar has to be pushing back. Okay, so the bar has to be acting in compression. That means that my force will be like this. Sorry, did somebody say something? Okay. Now I'm going to call this force DC because it goes from D to C. And it's right there, acting on my beam. Okay. Step number 2 is to apply the equations of equilibrium to find all of my external forces and reactions. This is actually really similar to a problem we did in class. So I think we should get this one done pretty quickly.
Hey David, can I ask a quick question?
Go ahead, sure.
So why is AX going in the left direction? Just curious.
We're just guessing. So right now my guess comes because since this force is acting in this direction, it's going to have a positive X component. So I kind of know that this X component has to be negative to counteract this positive one. Yeah.
Okay.
But it's just a guess. You know, you don't have to do it that way. All right. So who was this? Who asked the question?
Oh, sorry, me, Khalil.
Oh, Khalil. Welcome.
Thank you.
All right. Cool. By the way, Khalil, I'm playing a lot of Mario Kart because
Are you really?
I have nothing to do. So maybe after the class ends, you can send me your friend ID. All right.
Let's play. I'm down.
Yeah. I figured I can beat you up with statics, and now I can beat you up with Mario Kart. So two things. All right.
Double whammy. No, I'm pretty good, so we'll see.
We'll see. Step 2 is to apply equations of equilibrium. So we want to find all these forces. So we can't skip this step this time. So we know that the equations of equilibrium are sum of forces in the x direction equals 0, sum of forces in the y direction equals 0, sum of forces in the z, sorry, no, we don't have z, sum of moments at any point equals 0. So if you have the system, what should we start with?
Sum of moments in the y direction.
Sum of moments.
Wait, no. Yeah, sorry. Sum of
Okay.
moments.
All right, that's fine. So we'll start with sum of moments. So we say that sum of moments about any point should equal 0. What point do you want to choose? You want to choose point A, point B, or point C? I gotta label these.
Point A,
Okay, why A?
because then you don't, or then you cancel, so to speak, AY and AX.
Exactly, right?
So 2 unknown values.
Exactly. I choose point A because I cancel AY and AX. And not only that, if you look at this force will have a horizontal component acting right here and a vertical component. But if we're taking sum of moments here and the horizontal component is acting along the beam, we can also eliminate that from the moments, right?
I have a question.
Go ahead.
Why wouldn't you take it from B?
So my problem is if I take my sum of moments at B, I'm going to have this AY, which is unknown, and I'm going to have this FDC, which is also unknown. So I won't be able to solve for them. Does that make sense?
Yeah, that makes sense.
Yeah. So when you want to choose your point to run a sum of moments, always choose the point that has the most forces acting on it, because that way you can eliminate those forces. As long as those forces are unknown, you can eliminate them. So I'm going to defer to Yannick's judgment this time and take my sum of moments at point A. So at point A, none of these will count because the distance is 0, so there's no moments. So what do I have? I have a force of 400 pounds at a distance of 4 feet. And this is causing a clockwise rotation, so I'm going to give it a negative value. I also have a vertical component for this force, so I'm going to call this vertical component FDCY. I'm going to call the horizontal component FDCX. So I have this vertical component FDCY acting at a distance of 8 feet. Okay, and this will cause a positive rotation, which is counterclockwise. And all of this should be equal to 0. So, how many unknowns do I have here?
1.
Yep.
Yeah.
Okay, so I can solve for that y component. So I get that f dcy equals 400 times 4 divided by 8. That should be 200, right?
Yes.
Okay. Good. Now I can do sum of forces in the y direction because I have an extra y component. So if I do sum of forces in the y direction equals 0. Kind of sucks not having a board because I gotta go move my paper up and down. But basically I have this AY, which is positive. So I'm gonna write down this unknown AY, which is positive. I go back up here. I have this 400-pound force, which is negative. So I'm gonna write down minus 400 pounds. And then I go back here and I have this y component FDCY, which is 200 pounds, and it's positive. So plus 200 pounds. All of this equals 0. So now I can solve for AY. So what is AY? AY should be equal to 400 pounds minus 200 pounds. How much is that? 200 pounds. Right? So far so good?
Yes.
Okay, good. So I did some moments, I did some forces in the y direction. Now I can do some forces in the x direction. And you'll see that even though it looks like we have two unknowns, we actually don't. So let's look at that. We got some forces in the x direction. I have negative ax, I'm going to write it down. And then I have positive the x component of FDC. So I'm going to write plus FDCX. Now you might think, wait a minute, we have two unknowns, how can we solve this? But we don't actually have two unknowns because we know the geometry of this beam and we know the y component of this force. So treating this as a force vector, we know that FDC has the same direction as the beam itself. That means that the y component FDCY will be equal to the y displacement in terms of this beam. So we use the slope method. We don't really need an angle here, but we use the slope method. We know that horizontally this is 8 feet and vertically this is 6 feet. So what would that slope be? Well, I got 8 in the horizontal, 6 in the vertical. I can reduce it to 4 in the horizontal and 3 in the vertical. If that's the case, what's the hypotenuse? And if you don't know this, you can use Pythagorean theorem, but for a right triangle, I'm going to kind of make it quick for you. If one side is 4, one side is 3, the other side has to be 5. The hypotenuse has to be 5, okay? If you don't know how to get that value, that's fine. Just use Pythagoras theorem. You got 3 squared plus 4 squared. Take the square root of that, and it'll give you 5. Any questions with that analysis so far? Okay, good. So this y component is the same as FDC times 3 over 5. This x component is the same as FDC times 4 over 5. So how can we relate FDY to FDC? Well, you can write it down here. The y component is FDC times 3 over 5, and we know that this is equal to 200. Which means that the total force FDC will be equal to 200 times 5 divided by 3. So that's 1,000 over 3. How much is that?
333.3333.
Okay, 333. So now that we know that, we know that the x component will be equal to the total force times 4 divided by 5 using the slope method. So I'm going to write it down here. I got negative ax plus the total force, that's 333.33333 pounds. And then using the slope method, I get that's times 4 divided by 5 to get the x component. And all this equals 0. And now when we look at our problem, we only have one unknown. So all we have to do is solve for that ax. In this case, ax, I'm going to move it to the other side to make it positive, is equal to 333 times 4 divided by 5. So how much is that?
266.
Can you say it again?
266.4.
Thank you. Okay. So it looks like we did a lot of work, but we're actually still only on step 2. So, you know, sometimes we gotta gauge our time a little bit. I have a fluid mechanics review session at 8, but I want to finish this problem before I go to fluid. So let's try to rush through this problem so we can actually finish it. So we found all of our external forces, right? So let me see. If I were to draw my free body diagram again, I have an AY force of 200 pounds. An AX force of 266 pounds. I'm being very generous with rounding, so you don't have to be like that. I just kind of don't want to get a mess up numbers. We have this FDC, and I'm just going to split it into its components. This FDC has a Y component of, how much was the Y component? Was it 400? 200?
I think it was 200.
Okay. And then we had an X component of 266 pounds. And then we had a force of 400 pounds acting right down the center. Remember, that force was actually a product of a distributed load. Let's keep that in mind. Okay? We want to find the internal forces at point B right here. So step number 3 will be to select your point. We already did, that's point B, and then make a cut that goes through that point. So just as a general conceptual question, is my cut going to be vertical like this, or is it going to be horizontal?
Vertical?
Vertical.
Exactly. You always want your cut to be perpendicular or normal to the axis of the beam. So in this case, my cut is vertical. So I'm going to end up with 2 sections, one section on the left, one section on the right. And now you notice that the forces on the left and right are actually going to be pretty similar to each other. So regardless of which section you choose, your answer should still be the same. So which section do you guys want to choose?
Section on the left.
Okay, so let's choose the section on the left. So we're going to choose this section. If I were to draw this section, I have about 4 feet of a beam with a 200-pound reaction force in the y direction, a 266-pound reaction force in the x direction, and then I have this distributed load. Now this cut is only 4 feet long. So this distributed load, which has a magnitude of 50 pounds per foot, can now be reduced into a point force, which is equal to 50 times only 4 feet. So how much would that be?
200?
Yep. And again, this is half of the beam, and this is a rectangular load, so the actual force should be equal to half of the force, which 200 makes sense. This is a rectangular distribution, a rectangular load, so what's the distance from the left to where that 200 pounds are acting on?
2 feet.
Yep, that's correct. Okay, I can draw my internal forces. I have a normal force at point B. I have a shear force at point B, and I have a bending moment. Remember, I'm assuming that these internal forces are always going to be positive, in the sense that tension, clockwise, and smile. That's all it is. Okay. So now that I've identified my internal forces, I can go ahead and solve for those internal forces by applying the equations of equilibrium. Okay, so if we look at the system, let's start with the easy one. Sum of forces in the x direction, I'm going to set positive from left to right. Sum of force in the x direction equals 0. So what do I have in the x direction? From left to right, I have 266 pounds in the negative direction. So negative 266. And I have this normal force in the positive direction. So plus my normal force, this equals 0. And this tells me that my normal force is equal to 266 pounds. Okay? Any questions with this step?
No.
Good. So let's go ahead and take our sum of forces in the y direction equals 0. From left to right, I have a 200-pound force that's positive. I have a 200-pound force that's negative. And I have my shear force that's negative. All of this equals 0. Look at that, 200 minus 200, that's 0. Therefore, my shear force is equal to 0. In the other example, we didn't have a normal force. In this example, we don't have a shear force. But that's okay, that's normal. And now I can look at my bending moment. Sum of moments. And I'm going to select my moments at point B equals 0. I have a 200-pound force acting at a distance of 4 feet and making a clockwise rotation, so negative. I have a 200-pound force acting at a distance of 2 feet, making a counterclockwise, so positive rotation. And then I have my bending moment, which is counterclockwise, so it's positive. All of this equals 0. So now I can solve for my bending moment. My bending moment is equal to 200 times 4, that's 800, minus 200 times 2, that's 400. So 800 minus 400 is 400 foot-pounds. And that is my bending moment. Any questions before we wrap up?
No, that was very clear.
Cool. Kate, you good?
Yes, sir.
Gabriella and everyone else?
Yes. Okay.
Yep.
Okay.
Yep.
All right, cool. Well, thanks for coming to this session. I gotta head out because I have my fluid mechanics session here too. So anyway, thank you. I appreciate it. And we'll have another session, same time on Thursday of next week. Oh, wait a minute. We have a test, right?
Yeah.
Oh, let me think about that. I'll make an announcement or something. I'll post an announcement. I'll think about it. All right. See you guys.